In the last video, we looked at a basic example of inheritance, and we saw that that basic example did not do what we thought it should do. So let's revisit what that looked like. We had a class shape, we have a class circle, we have a class rectangle, and each one has a method called area, and the methods seem to be implemented the way that they're supposed to. And if you did this in Scala or Java, if you wrote this exact same code, basically, everything would be fine. Clearly in this case, it's not, because all the values that it printed out were 0. So it turns out there are two things going wrong here. The first is the fact that we passed this by value into here. And to understand why that is problematic, it helps to realize that when you pass by value, you're making a copy. Okay? So when we make a copy, and we're making a copy of just the shape. So whatever it is we pass in, we get kind of the shape part of it. Well, how big is shape? And similarly, how big are circle and double? And rectangle. Okay. With that written, we compile, we run. Shape consumes 1 byte. Guess it has to consume some amount of memory because shape doesn't store anything inside of it. Really, you could almost picture shape as taking no memory whatsoever, but then it wouldn't actually be an object. Circle has a single double inside of it, and so it uses 8 bytes, and rectangle has 2 doubles inside of it, so it uses 16 bytes. And the question is, so what happens when you call this function and you pass it a circle? Well, literally the first 1 byte of circle gets copied into S, and that's what's available here. So that's our first problem. If you're ever going to use polymorphism, if you're going to pass something in as a supertype, you either need to pass a reference or a pointer. Now, because I am not intending to change this, I'm actually going to pass in a const pointer. However, if I try to compile, we will be reminded of things that we saw in the earlier videos on const, the fact that this isn't going to work. I have to change my code here and make it so that all of my areas are also const, and then all of these. Now that's happy. But I still get 3 zeros. Okay. Why am I getting 3 zeros? The answer to this deals with the fact that methods in C++ are not, by default, virtual. Now, that might be a keyword you haven't heard, because when you work with Scala, Java, and a lot of the other similar languages that are out there, everything is virtual by default. And what does that mean? Well, when you see an area in shape and then another area in circle, you're kind of assuming that this one overrides this one. But it turns out that's only true if the method is virtual. In virtual methods, when you have a call, like this call here, instead of calling it on the type that's listed here, what's called the static type, it actually looks at the runtime type of this value and calls the appropriate method. Like I said, in Java and Scala and other similar languages, that's the default behavior. Okay? And so in those languages, this would be doing what it's supposed to. But in C++, it turns out because being virtual has an overhead to it, there are costs to things being virtual. For that reason, in C++, things aren't virtual by default. So when you write it this way, if you don't use the virtual keyword, it turns out that this is just another area function. It happens to have the same name as this one, but it's not overriding that one. Now, if I had a circle object, so if down here, if I said c.area, I would be calling the version on circle because the static type of C is circle. And this is where you have to differentiate between static type and dynamic type. The static type is the type that is actually written in to the code. Okay? So all S's have a static type of shape. However, when we pass them in, if we pass in a circle, it'll have a dynamic type of circle. If I pass in a rectangle, it'll have a dynamic type of rectangle. And how do we get that? Well, we put in the virtual keyword. And now I get the results that I was expecting. You'll note that I only had to put virtual in one place. Virtual is inherited as soon as the superclass says that it's virtual. Everything below it will also be virtual. However, it's a good idea to put things here. Otherwise, when these things are spread across multiple files, someone looking at the code might not realize, because in reality, these would be much longer classes. They would be in separate files, and someone looking at area in circle might not realize that the area in shape was virtual and might not realize the one in circle is virtual as well. C++11 also includes an override. We'll have to see if this is happy with the relative position to const. Note that unlike the override that is in the Scala language, this override goes at the end after the function, not before it. Okay, so now we're getting the behavior that we want. But you saw there were two things that we had messed up originally. One was passing the value in by value, as opposed to passing a reference either through a reference type or through a pointer type. And the second was the fact that the method wasn't declared as being virtual. Okay. You'll notice something else that happened here. And in fact, this highlights at least part of the reason why virtual is not the default. Notice what happened to all the sizes. All the objects got bigger. The shape is now 8 bytes, the circle is 16, and the rectangle is 24. And it turns out that that virtual, when you add the virtual keyword, as long as you have any single virtual method in there, you have to have what's called a vtable associated with the class. And every object now has a pointer to the vtable. So we added the overhead of an extra pointer into every one of our objects. Once again, that happens by default in languages like Java. The compiler might optimize it out in some cases, but that's the default, and you don't really have much control over it. C++ tries to avoid such things, and so they give you the choice of making things virtual. There's one last thing that at least I'm unhappy with, and that is the fact that shape really should not have an implementation. In Scala or Java, you would have said that shape was abstract and that the method area was abstract. We really, really kind of don't want this here. Well, and the question is, how can we do that? Because if I don't put it in there, I get a link error right now. And well, the answer to that is to make this not just virtual, but pure virtual. And the syntax, as you can see, is on a virtual method, you can say equals 0. And as soon as you do that, now the class shape is abstract, and so we get a different error, which says that we can't declare our variable s. Well, and that makes sense, because s is a shape. Shape has an unimplemented method. What would happen if we called area, which is exactly what this is going to wind up doing on that shape? Because it's not implemented, we would have an error. So I have to not declare the value s, and now it compiles and it runs. Okay. This is the version of the code that really we ideally wanted. We want the area method to be virtual. We want it to be a pure virtual method with no implementation. And then the versions in circle and rectangle are also virtual. They specify that they override. That way, if we do something silly like put an argument in here, the compiler will give us an error message about it. But we have to realize that as soon as we make things virtual, we pay an overhead, our objects get bigger, and it turns out that vtable lookup is an indirection, which actually slows down the call as well.